Hello everyone. Myself Satyam Kumar and my colleagues Sarthak Singh, Sarthak Sinha, Sarvottam and Saswat. We are here to let you know about Francis Turbine. Then the Francis turbine is a type of water turbine. It is an invert flow reaction turbine that combines radial and axial flow concept. The turbine is located between the high pressure water source and the low pressure water exit. Usually at the base of a dam, Francis turbines are used frequently in hydroelectric power plants. In these plants, high pressure water enter the turbine through a snail shell casing. This lowers the pressure as the water curls through the tube, but the speed of the water is maintained. Francis turbine is the most common water turbine in use today. The speed ratio of Francis turbine speed ratio varies from 0.6 to 0.9. These turbines are divided into two types: inward radial flow and outward radial flow. Francis turbine can be held in the form of radial flow turbine. Next slide. The main components of modern Francis turbine. First one is penstock. The penstock is used to drain the water from the source to hydro turbine in the powerhouse. Penstock diameter are between 1 and 10 mm. The speeds of different turbine units range from 17 to 1000 rpm. A wicket gate around the outside of the turbine's rotating runner control the rate of water flow through the turbine for different power production rate. Penstocks are pipes or long channel that carry water from the hydroelectric reservoir to the turbine. Inside the actual power station, generally they are made of steel and water under high pressure flowing through the penstock. Next slide. Second one is spiral casing. A spiral casing passes for directing the water from penstock around a water turbine and into the rotor. The spiral casing is the inlet medium of water to the turbine. The water flowing from the reservoir or dam is made to pass through this pipe. Spiral casing is an important component of Francis hydro turbine for the even distribution of kinetic energy. Along the stay and guide vanes, the fluid flow around the runner is dependent on the flow condition of a spiral casing. The shape of casing play an important role in proper flow distribution. The spiral casing is an important component Francis hydro turbine for the even distribution of kinetic energy along the stay of guide vanes. Next slide. The next is guide vanes. The guide vanes are the primary function of guide vanes to vane is to convert the pressure energy of the fluid into kinetic energy. It also serves to direct the flow at design angle to the runner blades. Guide vanes are fixed grooves found in the turbine that help direct water, gas, or air around band at maximum efficiency. As impeller increase or decrease the flow of distribution through a system, guide vanes ensure that the substance is passed evenly and as smoothly as possible. A guide vane cascade is developed for the study of flow in the distributor of flow specific speed Francis turbine. Velocity and pressure measurement are done with Reynolds number 1.5 to 0.7 at 80% of BP flow as in the reference prototype turbine. The guide means consists of number of blades that that can be adjusted in order to increase or reduce the flow rate through the turbine. The guide vanes govern the water flow rate and ensure that power production is synced with demand. In additional, guide vanes control the flow. Next, next slide. This is the diagram of guide vanes. Next slide. Next slide. Yeah. Now governing mechanism in Francis turbine. Basically, governing mechanism is used to control water flow rate and make sure that power production is synchronized with power demand. Apart from controlling flow rate, guide winds also control flow angle to inlet portion of runner blade. Next slide. This is the main component of modern Francis turbine. Next. Yeah. Now, runner and runner blade. Basically, runner blades are the of heart of any Francis turbine. These are the center where the fluid strike and the tangential force of the impact causes the shaft of turbine to rotate, producing torque. Close attention to the design of blade angles at inlet and outlet is necessary as they are major parameter affecting power productions. The runner blades have two parts. The lower half is made the shape of small bucket to rotate the turbine by using the impulse action of water, while the upper part of the blades use the reaction force of water flowing through it. The runner rotates through these two forces. Next, this is the runner blades and runners, which we use in Francis turbine to rotate the yeah to get the electricity. Next slide. Now, last one is the draft tube. The draft tube is an important component of Francis turbine which influence the hydraulic performance. The pressure at the exit of the runner of the reaction turbine is generally less than the atmospheric pressure. The water at the exit cannot be directly discharged to the tail race. A tube pipe of the gradually increasing area used for discharging water from the exit of the turbine of tail race. This tube of the increasing area is called draft tube. One end of the draft tube is connected to the outlet of the runner. However, the other end is submerged below the level of water in the tail race. This is the diagram of draft tube. Now, my friend Saswat Mishra will continue from this.
So this type of draft tube is straight divergent tube and not be able to give sufficient increase in air separation problem. It has the solid conical core in an entire central portion of the tube, thus allowing a large exit area without excessive length. Its central cone arrangement is made to reduce the whirl action of discharging water. It is suitable where water leaves running with a whirl velocity. This reduces eddy losses and also increases the life of draft tube. The efficiency of Moody spreading cone is around 85%. Next slide. Now let's discuss another type of draft tube which is known as simple elbow tube. So the simple elbow tube has a circular inlet and outlet shape as the diameter of draft tube should be as maximum possible. but at the same time flow separation should not take place. The length of draft tube must be more. Do you have definitely length in such case is the draft tube must be bent. So the maximum efficiency of a simple elbow tube is around 60%, and therefore they are rarely used in general use case. Next slide. Now elbow draft tube having a circular inlet square outlet. As we have seen on the previous slide, the simple elbow draft tube has a circular inlet and outlet, and this type of draft tube having a square outlet. This type of draft tube is very useful where large excavation is necessary. This has larger cross section at outlet which recovers more kinetic head at outlet. This generally used with Kaplan turbine and it has efficiency of about 70%. Now my friend Sarthak Singh will continue.
So this is the velocity triangle. So in turbo machinery, a velocity triangle or a velocity diagram is a triangle representing the various components of velocities of working fluid in a turbo machine. Velocity triangle may be drawn from both the inlet and the outlet section of the turbo machine. The vector's natural of velocity is utilized in the triangle, and most basic form of velocity triangle consists of tangential velocity and the absolute velocity and the relative velocity of the fluid, making up these three sides of triangle. As we can see here, the lower one is your outlet, and the upper one is the inlet triangle. A general velocity triangle consists of following vectors, which is v, which defines absolute velocity of fluid; u, blade linear velocity; v1 and v2 are the absolute velocity at entrance and the and the exit of from inlet and the outlet; alpha 1 and alpha 2 are the guided vane angles; beta 1 and beta 2 are vane angles, angle made by the relative velocity vector Vr, and n is the revolution per minute of runner. Next slide. Can you go to the previous slide, Sarthak Sinha? So basically, the significance of velocity triangle is to illustrate flow condition. The corresponding status of flow is described by the flow velocity in order to identify kinetic energy differences. Flow velocity are determined according to magnitude and or direction. This is done with the help of velocity triangle. So basically velocity triangle are typically used to relate the flow properties and the blade design parameter in relative frame, basically rotating with moving blades, to the property in the stationary or absolute frame. Next slide, Ratakana. So this is energy conservation in Francis turbine. In this, as we can see, the total absolute energy is the difference from the pressure side to the suction side of the turbine, which is GH. The lower part of the diagram shows the pressure energy and the upper part shows the kinetic energy. On the RHS of the diagram, before reach the inlet of the GV, 95% of energy 95% is pressure 95% energy is the pressure with increasing of kinetic energy towards the GV inlet where several flow is dominating. Through this case the rotational energy increase to match the circumferential speed of the runner blade. Also, mediatorial velocity increases because the water is flowing towards the decreasing diameter. As a result, the PR energy decreases up to 50% to the total energy at the inlet. From the runner from the runner inlet energy is gradually converted to mechanical energy by the runner. Towards the outlet of the runner, the absolute pressure decreases below the pressure outside the draft tube and rotational kinetic energy decreases as we have studied theoretically. At the runner outlet, the pressure normally decreases to the valve below pressure ATM. However, the kinetic energy decreases from the runner outlet to the draft of the tube outlet, where pressure increases to the pressure of water level above the reference level. Next slide. So here we come to the efficiencies of turbine. The first one is hydraulic efficiency. It is defined as the ratio of power given by the water to the runner of the turbine to the power supplied by the water at the inlet of turbine. The power at the inlet of the turbine is more, and this power goes on decreasing as the water flows over the vanes of the turbine due to hydraulic loss of the vanes and are not smooth. So, as we can see here, its formula is power developed by the runner to the power available at the inlet. Now, the next one is mechanical efficiency. It is the ratio of power delivered by the water to the runner of the turbine and the power transmitted to the shaft of turbine. Due to mechanical losses, the power available at the shaft of the turbine is less than the power delivered, and its formula is given by power developed by the runner to the power available at the inlet. Next slide. The third one is the volumetric efficiency. Basically, it is the ratio of volume of water striking the runner of a turbine to the volume of water supplied to the turbine. And the last one is overall efficiency. It is defined as the ratio of power available at the shaft of the turbine to the power supplied by the water at the inlet of the turbine. Next slide. Now, my friend Sarvottam will explain you about the cavitation.
Now we continue from cavitation. The cavitation problem in hydraulic turbine is well-known problem produced by bubble of a vapor when the pressure of the liquid is lower than the vapor pressure. This produces erosion in the moving part of the turbine, runner and shaft. It mainly occurs when the static pressure becomes smaller than the liquid vapor pressure. They may not remain in the state for long. Once the vapor bubble reaches a location where the local pressure is above the vapor pressure, they collapses and back to the liquid form. Next slide. So we will see what was the precaution take we against the cavitation. Precaution against lower pressure, which must ensure that lower our pressure should not be reached down the lower the vapor pressure. In the whole hydraulic system should not allow the fall below the vapor pressure for to keep absolute pressure head above 2.5 meter. We can also use different types of special material for providing a coating stainless steel aluminum rod. This may prevent our cavitation and longevity of the material. Cavitation may be avoided by selecting a runner of a proper specific shape, design, and for a particular given head. Next slide. Effects of cavitation: metallic surfaces are damaged and cavities are formed on the surface that can lower the life of our turbine. Due to sudden collapse of vapor bubble, considerable noise and vibration are produced that affect our overall efficiency of the cavitation, which overall reduce in the production of our power energy. Next slide. Hydraulic machine when subjected to cavitation, it causes roughening of the surface take place due to a loss of material caused by pitting. Vibration or take place in turbine which down overall efficiency of the our turbine, which lead to a reduction in power production. Actual volume of liquid flowing through the machine is reduced since the volume of the cavity is many times more than the volume of the water which they are formed, causing sudden drop in the output in efficiency. Next slide. How the appearance appearance in how we if the cavitation happen and sand or erosion damage, it causes the appearance of the our turbine petty hole formation take place on overall the surface of the turbine blades and overall hydraulic system, which causes roughness and which causes injury to the surface, injury to the person. Next from the now, my friend Sarthak Sinha will continue.
Hello. So thank you, Sarvottam. Now we'll discuss about NPSH. NPSH is net positive suction head. It is that value of it is the absolute value of suction. It is the absolute value of head available at the inlet of the inlet of the turbine. Mathematically, it is defined as the absolute pressure head at the inlet of the pump minus the vapor pressure plus the velocity head. As you can see in the given diagram, we are calculating NPSH as HA minus HV plus Z4 minus Z2 plus CS minus 1 into C2 square by 2G, where HA is the atmospheric pressure head minus HV small hv, that is the vapor pressure head, plus Z4 minus Z2, that is the height above the reference light at location 4 and 2, plus Cs, that is the loss coefficient, minus 1 into C2, that is the velocity at location 2. So we can easily get a relation between H2 and H4 by applying simple Bernoulli's theorem at location 2 and 3. On substituting the values, you can clearly see that we will be getting a term H2 is equal to H4 plus Z4 minus Z2 plus Cs minus 1 into C2 square by 2G. However, if we want to find the vapor pressure, we can substitute the value of H2 as HV plus delta H, where delta H is the difference in the heads of actual head and vapor head. On substituting the value of H2 as HP plus delta H, we can get the value of delta H as H4 minus HV plus Z4 minus Z2 into CS minus 1 into C2 square by 2G. This value is actually the net pressure suction head. Now, my teammates will be talking about the improvement in the development of Francis turbine.
As now we see the improvement take place from the historical time period. As with the time period, technology improvement take place. In same way, Francis turbine also improved. Modern Francis turbine now exhibit peak efficiency between 80% to 95%. Like example with the addition of draft tube in the end of the turbine, which increases overall efficiency of our turbine. A significant major improvement done by James V. Francis by using a scientific principle and mathematical knowledge he gained. He uses an analytical method that allow confident design of a high efficiency turbine that precisely matches the site of water flow and pressure water head. Next slide. Water wheel of different types has been historically used over hundreds of years. To power mill of different types like grinding, but they were relatively inefficient and not be overall weakened productivity. With the improvement in design and shape, we can now produce electricity and run our industry. Now, my friends Sasha will continue from the next.
So, as we have discussed earlier about Francis turbine, let's discuss about advantages of Francis turbine. So, the first advantage is now no head failure occurs still at the low discharge of water, and Francis turbine variation in the operating head can be more simply controlled. The mechanical efficiency of the Pelton wheel turbine decreases faster than the Francis turbine. And the next advantage is the difference in the operation head can be extra simply controlled in Francis turbine than in the Pelton wheel turbine. and the runner size of Francis turbine is small, and changing in head is easily controlled within the Francis turbine. Now next slide. Now we'll discuss disadvantages of Francis turbine. So the water which is not dirt free can cause extremely rapid wear in a high head Francis turbine. As a spiral casing is stranded, the runner is not simply available, therefore dismantle is hard. The repair and inspection are much harder reasonably. Cavitation is an ever-present hazard, and current losses are certain. So that's all for this presentation. Thank you.